Good morning, guys. So, today I want you to practice your homework problems. But before I do that, I just want to go over the last things that we talked about for chapter 22. The first of the last items we talked about is the point charge in an electric field. And just a short recap. The question is, if you have a point charge and you put it inside an external electric field, what happens to it? Well, it gets a force that's acted on it from the external electric field, and the force moves it. If you have a negative side and a positive side, the force, if this is a charged particle, if this is a positive charge, that force will tend to move it towards the negative charge because the electric field direction is in this way. And the force is given as, that's the force that is acted upon the point charge that is inside an external electric field, is given by the amount of charge on the charged particle multiplied by the electric field that is external in which you put the charge. So this idea is what was used to develop the inkjet printer. We discussed this in class, and I want to make sure that everybody understands how an inkjet printer works. So basically, you have an inkjet generator that shoots an inkjet through a charge generator and adds a charge to that inkjet, and then moves it through an external electric field that is in between some plates. So these are external electric fields, and if this is positive and this is negative, no, according to our arrow, this will be positive and this will be negative because the arrow is going inwards towards the negative. So if this is the positive charge, chances are it will get deflected towards the negative plate, and you have your paper here. So that's just a quick review. You guys should be able to describe this in more details. And then we also talked about a dipole in an electric field. Now, when you have a dipole, you guys remember what the dipole is: a system that has equal and opposite charged particles that are separated by a distance. So when you have this dipole will have a charge Q, and the dipole creates a dipole moment. So we have an electric dipole moment, which we defined earlier. Dipole moment, we called it P, and we said it's equal to QD, where Q is that charge and D is the distance between the charges that make up the dipole. So this charged dipole, when you put it inside an external electric field, what happens? So this is your dipole that is placed inside an external electric field. So you have electrostatic forces acting in opposite ends, in opposite direction, because one end is positive, so the negative charges will pull on that positive side, and then the other end that's negative will be attracted to the positive charges. So you have some force pulling this way, another force pulling that way, and that creates something that we call torque. And if you look up the meaning of torque, it's the force that acts in a circular path. For example, if you want to change the tire or your car, you put your wheel spanner, and the kind of force you apply to twist it is a torque. So the torque that is applied on this dipole is given as, we represent it as tau. This is a symbol, it's like a wiggly T, and that's TAO. And that torque is equal to that's equal sign, by the way. It's equal to the cross product of the electric dipole moment multiplied by that external electric field. Now, the beauty of this is that this is the principle that through which your microwave works. So how does microwave oven work? All right, I want you guys to look this up and teach me. But basically, what you will learn is that the food that you want to warm up contains water molecules, and water, H2O, is a dipole. So you have oxygen and you have hydrogen, HHO. So this is positive, positive, and this is negative, two negatives. So that makes it look like positive 2 and negative 2. So 2 elementary particles on the positive side, 2 elementary charges on the negative side, separated by some distance. That's your water molecule. Now, this water molecule, when you put it inside, when you put your food inside a microwave and you turn it on, what the microwave does is it provides some electric field that alternates inside of it. So the electric field changes direction so often, and as soon as it's changing direction, your dipole keeps moving in a zigzag pattern, like a flip-flop pattern, and it moves so fast that it gets heated, and that heats up your food. So the water molecules inside your food actually generate the heat that heats up your food in the microwave. And that is why when you place your food in a microwave oven and you heat it up, by the time you take it out, your food is like super hot, but you can touch the plate of the microwave and it's not hot. It's because the dipole inside the water in your food from the water molecules is what heats up your food in the microwave. All right, I need you guys to look it up and teach me. Okay, so and that brings us to the end of chapter 22. I just want you to walk over the homework problems. So let's look at these homework problems. You have, for chapter 22, you have homework problems 4, 23, and 34. So I need you to look at this. I will help you set it up a little. So for number 4, you have 2 charged particles that are attached to an x-axis. So first you draw your x-axis, and then you need to place the 2 charged particles. So particle 1 is at position x equals 6, and particle 2 is at position x equals 21. So let this be the origin. All right. Now we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So this will be our this is 21, this is 6, okay? And so we have one of the charged particles at position x equals 6. So this is particle 1, and the charge on it, Q1, equals negative 2 times 10 raised to power negative 7 coulomb. And the other charge, Q2, equals positive 2 times 10 raised to power negative 7 coulomb. Okay, so the question is that midway between the particles, what is their net electric field in unit vector notation? So what you have to do is find the midway between these two. How do you find that? You subtract 6 from 21, and then you divide by 2, and whatever you get, you add to 6. So you figure it out. Now, when you get your distance, what you want to do is calculate the magnitude of E1, and then you also calculate the magnitude of E2. You treat each one of them as a point charge. So you use the equation that says KQ1 over R square, KQ2 over R square. Now take note here, two things. One, this is not the magnitude. This is actually the charge that is the magnitude of the charge including the sign. So for E1, your Q1 is negative, but the direction is you're going from here to the center. So the direction is positive. So positive plus negative is negative. So whatever you get here will become negative. For E2, it is positive. This is positive, but the direction, electric field goes away from positive. So the direction will be this way. So this will be positive multiplied by negative. It will still give you negative. And then the question is asking for the net electric field. So the net electric field will be equal to E1 plus E2. So you add it all and you get your value, and that will be it. All right, let's look for the second problem, number 23. Let's see, what does it say? Now you guys know that you have these questions on that first document that has a lot of pages that I gave you. I put it on Blackboard. You just have to dig, or you can just pull it out of your textbook. All right, so problem 23 has a figure that shows two parallel non-conducting rings and their central axis along a common line. Ring 1 has a uniform charge Q1 and radius R. Ring 2 has uniform charge Q2 and the same radius. The rings are separated by distance D equals 3R. The net electric field at point P on the common line at a distance R from the ring 1 is 0. What is the ratio Q1 over Q2? All right, so this is interesting. You have two rings, and it's very important that you draw this accurately. The distance between the centers of the rings, you're given as D equals 3R. Okay, and you know that R is the radius. The rings are the same, so the radius for each is the same as the radius for the second one. So this is ring 1, this is ring 2. Now at what is P? The net electric, oh, okay, so there's a position P, and the net electric field at P equals 0. That is, i.e., at position P, E1 plus E2 equals 0. That is, you can rewrite that as E1 equals negative of E2. Okay, so all you need to do now is to write an expression to calculate E1 and write the same expression to calculate E2, and you make them equal to each other, and you're looking for the ratio Q1 over Q2. So if you write that, you should be able to calculate that ratio. So how do you write the E? Remember, for a charged ring, E equals QZ divided by 4 pi epsilon naught Z squared plus R squared raised to power 3 over 2. Okay, so if you say E1 equals negative E2, then you can rewrite the expression for E1 and make it equal to the negative of the expression for E2. So that is Q1R, right, because Z is R in this case. Z, remember, is the distance from the center to the point where you are measuring. So this is your Z for ring 1, and this will be your Z for ring 2. So Q1R divided by 4 pi epsilon naught, then Z is R, so instead of Z squared, you write R squared plus R squared raised to power 3 over 2 equals, and then you write the same expression. This will be negative Q2. Now instead of R, instead of Z for Q2, if this is from here to here is R, and from here to here is 3R, that means this will be 2R. This will be R and this will be 2R. So your Z for ring 2 will be 2R. So that will be Q2 multiplied by 2R divided by 4 pi epsilon naught. Your Z here would be 2R. So instead of writing Z squared, you're going to have 2R squared plus R squared, all raised to power 3 over 2. Now you have your Q1 here, you have your Q2 here. All you have to do is rearrange, and you see a lot of things cancel out. So rearrange and simplify until you get your Q1 over Q2. And that would be that for number 23. So you guys can solve it from there. Which other one? You have number 34. Let's see the question 34. Okay, question 34 shows a disk, and this disk has some surface charge density. What is the magnitude of electric field produced by the disk at a point where you have Z equals 12 centimeters from the disk? Well, this is very straightforward. Just plug in the value of the equation, rather. E equals sigma over 2 epsilon naught 1 minus Z divided by square root of Z squared plus R squared. That's it. You are given your Q, you are given your Z, do you have your R? 34. Oh yeah, you do have your R. So you really have everything, but remember to change distances to meters. All right, so that's it for the review for the homework. So I'm assigning the homework, and I want you guys to solve the homework problems today and have it ready by Monday. All right.